Hello, general chemistry students. This is the fourth video in our SLO 5.2, and here we're going to talk about the relationship between the Gibbs free energy with temperature. All right, so remember in Gibbs free energy, there's two parts of the Gibbs free energy, and that is the enthalpy term and the entropy term. And notice that the entropy term is where we see the temperature dependence of our free energy. All right, so if we look at this reaction and we know that the enthalpy and we know the entropy, we can calculate the Gibbs free energy. So here, even though we have a favorable enthalpy, a favorable entropy, we have an unfavorable enthalpy, and that leads to a reactant favor process. So we have a positive Gibbs free energy here. And so because we have a favorable entropy and an unfavorable enthalpy, that means that the Gibbs free energy is going to be temperature dependent. Okay, so the question here is, okay, so now at 298, the Gibbs free energy is not spontaneous, but at which temperature does the Gibbs free energy become favorable or spontaneous, right? And so we need to think about at which point does the Gibbs free energy change from positive, that it is now, to negative. All right, so to answer this question, what we would do is we would set the Gibbs free energy to 0. We'd set the Gibbs free energy to 0, and we would determine or we know the enthalpy, we know the entropy, and we can then solve for the temperature. All right, and when we do that, we get a temperature of 835.1 Kelvin. What that means then is that we raise the temperature to 835 Kelvin, and then this reaction becomes spontaneous. All right, so I'm going to give a few examples, and we're going to talk about why the correct answer is in fact the correct answer. So we're looking at these 4 reactions, and the question here is, of the following, which system shows a decrease in entropy, right? So a decrease in entropy. So we're going to look at each one individually and decide which one is decreasing in entropy. So in the first, in number A, we have a liquid that goes to a gas. So a liquid that goes to a gas is increasing in entropy. Increasing in entropy. All right, so we'll just draw an arrow indicating, okay, so A is not the correct answer. In B, we have a solid that's being dissolved in water to form ions. This results in an increase in entropy. All right, so solids dissolved into water is an increase in entropy. All right, so in C, we have 2 gas molecules that form 2 gas molecules. Here we would say that there is no change in entropy, just given the reaction we see. Or we won't know. In D, we have 2 gas molecules forming 1 gas molecule. The system is becoming less complex. So we can say that the entropy in that system is decreasing. All right, so we would pick D as our answer in which the system is showing a decrease in entropy. All right, so let's look at this problem. The question is we need to calculate the total change of entropy when 10 grams of ice melts at 25 degrees. The enthalpy of fusion is given as a constant, 6.01 kilojoules per mole. So what we need to do is we need to solve for the total entropy change at 25 degrees. Right, so remember, kilojoules per mole means that we need to convert our grams of ice into moles of ice. So we would take 10 grams, divide by our molar mass, which is water, 8.02 grams per mole. All right, and then we can multiply times our enthalpy of fusion, that's given in kilojoules per mole, and I'm going to just convert it right away to joules. All right, and so the units we get out, you can see, are joules. And we end up with 3,335 joules. Right, so that is the heat that's transferred in this process. But we want to know the entropy, and the entropy is the energy dispersal at a given temperature. So we would take 3,335 joules, and we're going to divide by the temperature in Kelvin. So 298.15 Kelvin. And this will give us our reaction in joules per Kelvin. Right, and if you calculate that out, you should get 11.2 joules per Kelvin. All right, so here we're going to find the temperature at which the Gibbs free energy becomes spontaneous. Okay, so we're going to assume that this reaction is not spontaneous, and we're going to calculate the reaction when it becomes spontaneous, or the temperature at which it becomes spontaneous. So remember, we're going to set the Gibbs free energy, to 0. We are given the enthalpy of the system, and we'll subtract from it T times the entropy of the system. And then we're going to, and then we're going to solve for T. Okay, so T is really a measure of the enthalpy of the system divided by its entropy. All right, and now we're just going to put in numbers. Remember, we want to keep our units consistent. So I am going to keep a consistent unit of kilojoules. So 131.3 kilojoules per mole. And I'm going to convert the entropy into kilojoules. So 0.1336 kilojoules per Kelvin mole. All right, and you can see from this that we're ending up with our answer in Kelvin, and that's what we want. And if you divide that out, you should get 983 Kelvin. All right, and this is a question where we really have to think about what values we need for a process to be spontaneous. So we're asked about a mole of liquid water. It's frozen in a freezer at -10 degrees. What are the relative values of the delta S of the system and the delta S of the surroundings? Is the reaction spontaneous? So we know that water freezes at 0, so we could say, yes, it must be spontaneous. So we could have this answer, or we could have this answer. It's got to be spontaneous because we have a lower temperature. Right? So the process of the system, we're going from liquid water to solid water. We would say that the system is going to be less than 0 or negative. And we would say that the surroundings is going to be positive. All right, and so if we look at all the responses, we would pick D as our answer. Here the system is less than 0. Here the surroundings is greater than 0. And we knew just because we had a temperature of minus 10 degrees that the process was going to be spontaneous. All right, so that is the end of our videos for SLO 5.2 having to do with the second law of thermodynamics. Thank you.